Right now, hundreds of miles above your head, thousands of satellites are moving through the vacuum of space at nearly 17,500 miles per hour. We often describe them as floating in zero gravity, as if reaching space means stepping outside the reach of Earth's magnetic or gravitational hands. But the reality is far stranger and much more dynamic. Gravity at the altitude of the International Space Station is almost as strong as it is right here beneath your feet, roughly 90% of what you feel standing on solid ground. Satellites aren't floating because gravity stopped pulling. In fact, every single satellite in orbit is falling directly toward Earth at every moment of its life. The only reason they don't crash into the ocean or smash into the dirt is that they are moving sideways so incredibly fast that the Earth curves away beneath them at the exact same rate they drop. To understand how this continuous fall creates a stable orbit, we have to look back to a brilliant thought experiment proposed by Sir Isaac Newton in the 17th century. Imagine standing on top of a mountain so tall that its peak sits above Earth's atmosphere, completely free from air resistance. If you hold out a cannonball and simply drop it, gravity pulls it straight down to the ground. If you load that cannonball into a horizontal cannon and fire it, gravity still pulls it downward at the exact same rate, but its forward speed carries it some distance across the landscape before it hits the ground. Now imagine packing that cannon with more gunpowder, fire the cannonball faster, and it travels much farther across the horizon before landing. If you keep increasing the horizontal velocity, something extraordinary happens to the geometry of the situation. Earth is not a flat plane, it's a giant sphere. For every 5 miles you travel horizontally across the surface of the Earth, the ground curves downward by about 16 feet. If you can fire the cannonball horizontally, at roughly 5 miles per second, a remarkable balance occurs. In the 1 second it takes gravity to pull the cannonball downward by 16 feet, the surface of the Earth has curved downward by those exact same 16 feet. The cannonball keeps falling toward the center of the planet, but the ground keeps falling away from it at the exact same rate. The cannonball is in a perpetual state of free fall, endlessly traveling around the planet without ever hitting the ground. This is precisely what an orbit is. This balance between forward momentum and gravitational pull explains why getting into space isn't actually about reaching a certain height. It's about reaching a staggering speed. Rocket launches spend a relatively short amount of time climbing vertically to clear the thickest layers of the atmosphere. Once they clear the heavy air, the rocket tilts over sideways and spends the vast majority of its engine power accelerating horizontally. For low Earth orbit, where many Earth observation satellites and space stations reside, that horizontal speed must reach roughly 17,500 miles per hour. If a satellite slows down even a little bit, its path bends downward toward the atmosphere. If it accelerates past that orbital velocity, its orbit becomes an ellipse, stretching farther out into space. If it reaches escape velocity, about 25,000 miles per hour, Earth's gravity can no longer pull its path into a loop, and the spacecraft breaks free into deep space entirely. Because an orbit relies on maintaining this exact sideways speed, atmospheric drag is the ultimate enemy of satellite longevity. Space doesn't end abruptly at a single line. The atmosphere simply grows thinner and thinner the higher you go. Even at altitudes of 200 to 400 miles, trace amounts of gas molecules still linger. As satellites collide with these sparse air molecules, friction subtly drags on the spacecraft, slowing down their horizontal velocity over time. As their speed decreases, gravity wins the tug of war, pulling the satellite into lower, denser layers of atmosphere where drag increases exponentially. This process, known as orbital decay, eventually causes uncontrolled satellites to plunge into the denser atmosphere, where intense friction heats them up until they burn up like shooting stars. To prevent this, active satellites and space stations carry small onboard thrusters. Every few months, they execute brief engine burns to boost their altitude back up, replacing the kinetic energy lost to atmospheric drag. Understanding orbit as an eternal high-speed fall changes the way we look at our night sky. Spaceflight isn't about escaping the fundamental forces of physics, it's about mastering them through precise velocity and orbital mechanics. When you see astronauts floating inside the space station, they aren't experiencing a world without gravity. They are falling toward Earth at the exact same speed as their spacecraft, living in a continuous, weightless drop around our planet. Every operational satellite orbiting Earth right now is locked in that very same dance, falling forever toward the ground, but moving so fast sideways that the world simply rolls out of the way.